Okay, perfect. All right, so yeah, diving in. My name is Mark Kurtz. I am the Director of Machine Learning for a startup called Neural Magic, where we specialize in neural networks and specifically being able to make them more performant, easier to use, and more cost effective. So feel free to connect with me on LinkedIn or Twitter, and also everything I'm going to go through inside of here, we have published in our GitHub. So if you'd like to play around with it, feel free. And yeah, if you have any questions, feel free to reach out to me. More than happy to walk anyone through anything. So going through today's agenda, we'll start off with a little bit on deep learning sparsity. So we'll spend quite a bit of time there, go through deep learning background, sparsification background, what is sparsity and what are we doing with it? What's the purpose? We'll go through some algorithms that apply for sparsification, as well as some ways to apply that and some methods to apply that, as well as the tools that we have available at Neural Magic to be able to apply all these to try and make that easier to do and fit into whatever you might be doing for a project, including our sparsification platform, Sparsu, SparseML, and DeepSparse. So I'll go through those a bit later. And then we'll go through some performance and actual use cases. So what does this look like whenever we actually try to apply it to some problems that we might be running into or problems that we're trying to solve, including image classification, object detection, and natural language processing. And then we'll close out with future work and any questions that anyone might have. So diving into deep learning background, as we can see on the right, we have a simple neural network here, which is trying to classify this cat at the top. So looking into this, neural networks started around 1943, and they've made steady progress into 2010. They're loosely based off the brain, where we're looking at each of these neurons and the connections. So within the brain, we have a bunch of neurons that are constantly trying to send signals to each other, and they're nonlinear in nature, meaning that we can't just do a single linear function to evaluate the entire network. So we have nonlinearities, we have spiking functions in the brain. For most neural networks, it's something a lot simpler. But the overall goal is to make sure that we have a nonlinear function to learn complex data. So here we're trying to classify this cat. It'll distribute signal throughout the network, and the weights in between are what we're going to be changing. So we're going to train on some data, test on the validation to see if the desired learn function that we have, so the weights that we train inside of here actually evaluate correctly and generalize outside of the training set. Right? It's really easy to make a database where you just look up every single answer. It's really hard to get a general model to generalize, especially whenever we're looking in computer vision and NLP, some of the more natural human-based paradigms. And to update these weights, what we're going to do is something called backpropagation SGD. So we're going to propagate the information all the way through the network, figure out whether or not we were correct. If we're not, well, even if we are and we're off by a little bit, we're going to backpropagate that error through the entire network so we can update every single weight in this network by a little bit to try and make it match what the expected output that we thought it should be, right? So here, cat, as we propagate it through, we want to make sure that it outputs cat. And if it doesn't, then we're going to propagate back the error so that it does predict cat. Moving on into this, the big breakthrough came from AlexNet, which was introduced in 2011, and it really kicked off the deep learning revolution. It easily won the image classification challenge at the time, considered to be the hardest deep learning challenge back then, ILSVRC, and they won this by using GPUs. And the reason why the GPUs were important is because it had increased the compute that they were able to use for this model, and that enabled a much larger model, meaning a more complex model and something that could learn more complex functions. And that's the interesting part about deep learning, which is that with enough data, it won't overfit, even with a large number of parameters. And this is why it's caught on so much, is you can just throw a ton of data at it and in a big enough model, and it will just keep generalizing. It won't start overfitting. It won't turn into that database where it's just memorizing the information coming in, but it actually still generalizes to the solutions and the functions that you're trying to map. So in this case, cat, it's not just going to memorize this picture. It's going to learn the features that make up a cat and therefore be able to predict cats. If a cat is slightly off to the left or right, different color, different orientation, things like that. So diving into the sparsification background, because of the lack of penalty for over-parameterization, right? We can just make these models as big as we can to a limit, right? They need to be able to be trainable, meaning they need to be able to fit onto GPUs. But the models continue to increase in size. How big? Well, the largest one now is 530 billion parameters. That's 2 terabytes in total size just for the parameters. It's a huge model. Takes a supercomputer to train it. And it's no surprise that given all of those parameters, not all of them actually matter. So this is where sparsification comes in. It actually takes advantage of this fact. So sparsification encompasses several algorithms, all focus on removing the redundancies that come from over-parameterization in these neural networks. All right, as we make these networks bigger and bigger, it makes sense that we don't need all of those in there, and sparsification is taking advantage of that. The result after sparsification, the reason why we want to do this is that we create more efficient models. The end goal would be, you train it on a really large GPU or a system of GPUs, and you can hopefully simplify it and make it more efficient so you can deploy it on your computer rather than needing all of those GPUs to run it again. So you're able to run faster for quicker and cheaper responses. It enables smaller models for deployments on phones and other edge devices. And it reduces energy consumption, leading to both environmental and cost savings. So going back to our cat example, a lot of sparsification actually goes into even what's running on your iPhone or your Android currently. Anytime that you take a picture, and as long as you're signed up for one of the Photos apps, it's constantly running neural networks on top of that to try and figure out what's in the images, so that whenever you go back to search for it, you can find all the pictures of your cats. The more efficient you can make these models to be able to detect cats and dogs and all these other classes, the cheaper it is for both Apple and Google to be able to deploy this, as well as the faster it can get back to you so that you can actually search for those photos. So let's dive into some of the algorithms. Specifically, we're going to look at pruning first. So when we're looking at pruning, what we have is a short neural network here, right? So we have our input layer here, our output layer here, and one hidden layer. We have a lot of connections in between. And what we're going to do is actually remove those connections. This is what we refer to as pruning. So the surprising part is that for neural networks, most weights are actually useless, so we can actually do this. The pathways that were important for a large optimization space, as we were training, right, we want to be able to explore a really large optimization space so we can hopefully converge to a really good solution. Those become unneeded as it converges. So you can think of it as we're kind of going down this lost surface, we're just removing the pathways that we didn't use to get to the point that we're at. So pruning is removing the unused connections, and that's what we see here. All these connections that were removed, these were the unused ones. And this results in sparse models with fewer parameters. So overall, we need less compute and storage for the model. And how many connections? The surprising part, you can actually get rid of most of these networks. You can get rid of 95% for our animal classifier that we were talking about and still keep 99% of the same accuracy. And this is on the ImageNet challenge, challenge, the ISL VRC challenge. Really, really challenging problem. We can actually get models that are 95% sparse. We can get rid of 95% of that network and still keep the same accuracy. And this is what's the really surprising part. So we can leverage that for a lot of efficiency gains. And to dive into pruning a little bit more and get a little bit more advanced in it, pruning is sorted into unstructured and structured. So what we just looked at was unstructured. So that means that we didn't change the shape of the network at all. It kept the same number of nodes at each layer, and we just removed the connections between those nodes. Structured, on the other hand, like channel or filter pruning, which I'll show now, removes whole nodes. So for example, you can see that we got rid of a few of the channels here. Instead of just removing the connections in between, we removed whole nodes. And let me go back for a second to talk about this. Channel, so the reason why there's a difference here and the reason why they're explored differently is because channel pruning is easier to get speed up on, but because you're removing whole nodes and therefore a large amount of connections with each node, you end up affecting accuracy more. So generally, unstructured works out better because you can get to a much higher sparsity. That 95% that I quoted drops down to 40% whenever we're looking at a structured technique. And then diving in real quick into which weights to remove. those can vary with the algorithm. So a standard algorithm is magnitude. What we're going to do is look at all of these connections here. And as the model is converged and trained, what it's actually doing is regularizing the weights that don't matter. So those weights get close to zero. And all that we're going to do is remove the ones that are closest to zero. There's also something called movement, which is that as we're training, it's looking at weights that are trending towards zero. So which ones are moving to zero, which ones are getting regularized. So which of these connections does it look like the training process is trying to remove, and then it removes those. And then finally, there's Wood-Fisher and other second order methods. And what they do is they actually approximate what the effect of removing every single one of these connections, try to approximate that and see how much each one of those connections would affect the loss if we remove them. So these can actually be really accurate, but they're pretty costly to run. So diving into quantization, which we can see on the right, we have our same neural network, and you can see that we made it smaller. Both the nodes and the lines, the connections got smaller. So what this leads to is that for most neural networks, for neural networks, most weights are also too precise. The precision needed for those small weight updates, right, as we're talking through SGD and backpropagation, are no longer needed as we're just doing the forward pass. So since we're not updating the weights, we can actually approximate the forward function, so coming through, with a simpler function. And that's what quantization does. So it's going to remove the unused precision. Specifically, what we're looking at is we're going to, for both the weights, these connections in between, and the activations, the nodes that we see here, we're going to quantize them. And normally they're kept at floating point 32 level precision. And we're going to break that down into int8. And we can generally do this for free and get back to the same accuracy as the model, as long as we're going to int8. This gives us a 4x reduction in size, memory, and even further gains in compute, depending on the hardware. And finally, some advanced techniques can also push this even further, not just to int8, but also to int4 and int2. int2, getting really close to just a binary network where you just have a bunch of Booleans running through the network. It's actually pretty impressive that people can get down to that. And then just covering a little bit more advanced topics in quantization. So quantization can be broken down into static and dynamic. So static is where, because we need to compress these activations, we're going to look at a sample distribution. So we're going to run a bunch of samples through the model and look at every single activation and figure out what the distribution looks like for the input to each activation in each layer. And we're going to collect those. And then what we can do is use that to compress those activation ranges when we're actually running. So every time we see an input, we can use that statistical distribution to be able to compress from FP32 into int8. And then we additionally have dynamic. So this is actually not going to do any of the sample distributions. It's just going to, as information comes in, it's going to collect all that information and then essentially do an average across that, and then do your interpolation from FP32 into int8. And just a quick note on those, why there's a difference. Dynamic is generally better for accuracy recovery because it is dynamically changing for every input, but static is better for performance because you pay a penalty for that dynamic change. And then last algorithm that I'll go through is distillation. So distillation guides the training process to enable better accuracy in smaller models. So what I mean by that? Well, what we have is a teacher network that we're going to use to generate the correct outputs for the student to learn from. So we have a teacher network, which is a bigger network, and we have our student network down here. They both get the same input, same image input. So cat, for example, from our earlier one. And then what the teacher is going to do is tell the student what the output is, and we're actually going to combine that into our loss function. And then update our weights based on what the teacher said it should be, what the teacher said the answer should be. What this leads to is an effect where we're actually smoothing and correcting the loss surface. So for example, a teacher can guide a classification model to not only classify the cat correctly that we're talking about, but that's also related to dogs. So rather than just telling the model that we're teaching, that we're trying to train, that this is not a cat, we can also tell it that it is visually similar to a dog, and therefore learn some more information and converge hopefully closer to the accuracy of that teacher, because since that model's larger, it's going to have a higher accuracy. It's traditionally used for creating smaller networks. meaning that it's getting rid of layers or channels. So you can think of, getting rid of 3 of these channels and you have a much smaller network. But it's increasingly being used as sparsified networks with quite a bit of success. And then diving into a little bit more of the advanced concepts. So we have a few different types. We have something called response, which is what's illustrated here, where we're just going to distill based on the outputs. We're going to look at the output from the teacher, the output from the student, and try and match those outputs as best we can. We have feature, which is where we're going to ignore the output, but we're going to look at the intermediate activations for every single model. So looking at kind of this middle layer and this end layer here, we're going to add both or do a difference between both of these so that the goal is to make sure that our student matches the teacher at every single step. And then finally, there's relation, which is distilling on relationship between feature maps. So what this looks like is instead of trying to match the outputs exactly, it's going to try and find a relationship. So it's going to project into an embedding space. So essentially try to come up with some mapping function to say, to try and compress the information and simplify the information. And then it can do things like a dot product or just nearest neighbor to judge based off of that and update our loss accordingly. And so given all those algorithms, there are a few different ways to apply them. One is post-training, or what we call one-shot. So what this means is after we've trained that animal detector and converged on the training set, the sparsification algorithms are applied with a sample data set. So we're not going to do it while training. We have our trained model. We're going to use a small data set, a small sample, and then we're going to try and optimize the model just using that, right? So if we're thinking about quantization, we're going to run that small sample through to figure out what our distribution is at each activation so we can do static quantization. It's quick and fairly easy to apply. And it works well for dynamic quantization, but it currently does not work well for pruning. This is actually some new research that we have coming out at NeurIPS later this year. And we're going to be we're currently working on quite a bit more research on top of it and building out some products on top of it. So stay tuned for that. We also have training aware. This is where the optimizations that we're doing are the sparsity algorithms. We're going to apply those while training on the training set. So for pruning, for example, it would make sense that if you got rid of 95% of the network all at once, that might be a big hit to the model. It might not recover. But what we can do is, as we see each new batch coming in, wait for a little bit, wait for the model to converge and adapt to the fact that we took away some neurons or took away some connections. And that way it's actually readapting and readjusting all the weights so that we can take away 5% or 10% next time and make sure that we always have the weights that matter the least to the model, right? Waiting for the regularization to push those weights to the smallest if we're doing magnitude. And then we can just remove those. And that way we're iteratively doing this over a course of time, and the model is constantly adapting as we're removing this information from it. It does take longer and more iterations, but generally much more accurate at higher sparsity levels and even for quantization. So it works well for pruning and quantization. And then finally, we have sparse transfer. So this is where we're going to fine tune a pre-sparsified model onto a new data set. So for example, the cat, dog, and bird detector that we started with, that's a simpler problem than trying to solve something that does not only animals, but also vehicles and silverware and household utensils and plates and all kinds of things like that, right? The ImageNet data set actually has 1,000 different classes. So what we can do is train on that large data set and then do training aware sparsification on that large data set. So we can create this sparse model that now stores all the information that it took to generalize to all of these different tasks, potential sub-use cases and classifications. And then we can actually fine tune that model onto our specific data set while keeping the sparsity the same. And that actually works really well and actually generalizes better than standard fine tuning. And we have a couple papers out on that as well. But it's faster and easier than training aware, but not as quite as post-training, not as quite as easy as post-training, but definitely more accurate. So diving into the tools that allow you to do this. So with Neural Magic, what we're doing is we're building a sparsification platform around recipes. And what recipes are, they're just defining all these different algorithms that you can use and the hyperparameters that go along with them, meaning, when to apply sparsity, how much to prune, when to quantize, things like that. Those are all defined in a YAML recipe, a YAML file, just as kind of an easy to read text file instead of the code. So with Sparsu, what we do is actually we have the state-of-the-art recipes that we generate internally for sparsifying these models, and we push them up there so anybody can pull those down and try and adapt them to their use cases. And it's all open source, free to use. And additionally, we push up the pre-sparsified models that we create on large data sets, so people can just pull those down and do sparse transfer learning and get a really efficient model without having to put in all the research for how to sparsify the model. We just show you have SparseML. So this is where we have support for many of the state-of-the-art algorithms and integrations. So everything that I just went through, including the different types for each one, that's all implemented in SparseML. So you can use these recipes that I talked about to easily implement those on any training system that you might have. And you can do this all with only a few lines of code. So your training platform, no matter how complex, currently mainly prioritized on PyTorch, but no matter how complex, should be able to fit it in with just a few lines of code. And so it's going to modify any training graph to make sure that we can support that. And it's open source and growing. And then finally, Deep Sparse is the engine that we have that leverages all of the sparsity to be able to get the performance numbers, to be able to get that better performance. I'll go through some performance numbers after this. So it's the fastest CPU inference engine utilizing sparsity and free to use for community or research. And the big thing to call out is actually, remember how I talked about GPUs in the beginning and how those were leveraged to really be able to up the compute and up the processing power. Well, we can actually beat GPUs with a standard CPU with Deep Sparse by leveraging all of that sparsification technology and the redundancies in these networks. So let's go through some performance examples. So you have image classification, right? So we have a picture coming in, we want to classify it as a cat or a dog or whatever it might be. ResNet50 is a popular architecture for it. And what we can do whenever we prune and quantize it, and this is actually the one I was talking about that we can get to 95%. So we can remove 95% of the weights and quantize it. And we can get to 99% of the accuracy. So 99% of the time, we're going to classify exactly the same. But we're going to run it 6 times faster for latency. So if you're just trying to get an answer back immediately, 6 times faster. And we can also do 8 times faster throughput. So if you batch a bunch of items together, we can run those 8 times faster. So a significant performance improvement. And what this looks like is here is a dense unoptimized model. And here is the sparse quantized model up here. So 8x faster, significant improvement going from 324 images per second all the way to 2,500, almost 2,600. Some example use cases where you might use that is in manufacturing where you're doing defect classification, sorting, or product identification, right? Think a manufacturing line where you have a tray or belt coming through, a lot of products coming down, you need to quickly classify whether or not that product is a defect and be able to kick it off the assembly line. Additionally, retail is used a lot with visual search and product recommendations. So anytime you go onto Wayfair, I'm not sure on Amazon, they haven't put out too much research on it, but Wayfair definitely is big on it, where whenever you do a text search, it's actually using an image classification model to convert both the images for the products. And then it uses a text, an NLP model, which we'll go through a little bit, to convert that into an embedding space that they both share. So you can search for a red shoe, and that image didn't have to be classified. Somebody didn't have to go through and tag it as red shoe. It's just automatically going to know that. And then object detection. So this is where we're looking at not just trying to classify what is in the image, but where in the image it is, right? So we have 2 cats over here. Those are the red boxes. Duck down here is green, and then the dog as blue. So YOLO v5s and YOLO v5l are popular models for object detection. And a pruned and quantized YOLO v5l can achieve 95% accuracy recovery. This is actually something we're going to be coming out with some new results on very soon that increases that recovery. But it has 4x faster latency and 9x faster throughput. So what that looks like is YOLO v5l here going 4x faster, and YOLO v5s going, I think that one's actually 4.5x faster. But essentially what this means is that you can actually shift what used to be the Pareto frontier where we saw accuracy versus latency here. We actually shift that entire Pareto frontier by using sparsification. So you get a more accurate model at the same performance or a much more performant model at the same accuracy. So some example use cases for manufacturing, we have inventory management or warehouse utilization, right? So you're trying to make sure that you don't have too many people in the same area, or trying to make sure that you have enough product stocked, things like that. You can tell how many items are in an area. Retail, there's a ton of product placement, traffic analysis. You can see how many people are coming through. We actually talked with a company that during COVID, they were actively trying to monitor people that were coming in and walking throughout the park to make sure that they were keeping within the 6-foot distance recommendation at that time. And then NLP. So what we're looking at is text coming in, and we're just trying to classify that text in different ways, right? So you can see here some positive and some customer support. So we're just trying to, here we're doing token classification where we're just trying to call out what each different word means and if it's a positive signal or they need to get to customer support, things like that. So BERT and BERT large are pretty popular models for NLP. Pruning quantized BERT large model can achieve 99% accuracy recovery, 8x faster latency, and 11x faster throughput. And what this looks like is actually, here's the original BERT large. Here's some other models, BERT base and Distilbert. Distilbert is a really popular model because it's a lot faster. But you can see this accuracy difference here, right? And that accuracy difference can cost you a lot in terms of customers or just, you know, incorrectly classifying or incorrectly responding to a customer. So you lose business. But with the pruning and quantizing that BERT large model, what we can actually do is keep the same accuracy and match that much smaller model in performance. Some example use cases in retail. We have review sentiment analysis. So if you're Pepsi, probably constantly crawling Twitter to see whether Pepsi is generally being mentioned as positive or negative. We have question answering. So, you know, if you're going through documentation search or you're just doing any kind of search, that'll get into question answering, knowledge retrieval. And then semantic search, which actually gets interesting where you're trying to not only just do a lookup, but also trying to tell what the user means. This gets into what I was talking about earlier with Wayfair, where you can say, I want a very large laptop or a very fast laptop, and that'll automatically map to your fastest product that you have, or your fastest laptop product that you have, without you having to classify all of those and label all of those yourself. And then just real quick, calling out some future work. So we have more use cases and improved models coming out. On NLP, we have information retrieval, summarization, translation, generation. Generation is what you see a lot for the large language models, where you can have it generate a ton of text. It's really useful for content augmentation. So you have it write while you're typing along, you can have it give hints as to what you want to do, as well as auto code completion, really popular with CodePilot through GitHub. And then computer vision, we have pose detection, semantic segmentation. So these are going a little bit further and trying to classify essentially every pixel in the image rather than just putting bounding boxes around the interesting objects. Additional compression methods we're also adding in. So we're adding in better distillation, more support for structured techniques, and further pruning improvements as we develop more technology and more research. And then additionally, we have the one-shot implementation. This is what I was mentioning earlier that we have research coming out on. Really excited for this to come out, and hopefully, well, we have really, really good results. So I'll leave it at that. And then we also have more general and improved performance with deep sparse. So we have faster models and expanded model performance support. And currently, we've only been able to support x82 devices. So think, you know, Intel and AMD chips, so laptops, desktop servers. ARM is now what we're really working hard on to make sure that we can also support phones and more edge devices. And then finally, we're focused on ease of use and automation. So updating and simplifying our docs, and then automating our Sparsification as a service. So think all this complexity around the recipes, be able to completely automate that so you can just plug it in a model and it'll do all the hard work for you so you can get back to what matters, which is getting a performant model for your use case and be able to iterate on that. All right, so we can jump into discussion Q&A. So we have a few questions that came in. So looking at, does integer overflow, I think, is integer overflow a problem with quantization? Yes and no. It depends on how you do quantization. Generally, it's accounted for because as you're accumulating with the integers, what you're going to do is accumulate into an int32. And then what you're going to do is once you're in N32, convert to FB32, and then requantize after each layer. So it costs a little bit of performance, but this avoids that integer overflow problem. And then additionally, we had a question that came in, which was, does the sparse engine also implement architecture-aware optimization? and take advantage of hardware like tensor cores, for example. So great question. We don't have anything on tensor cores currently, but we actually do have a lot of technology that goes into the Deep Sparse engine that does exactly this for CPUs. And what's really interesting is we have something called tensor columns. And this is the concept of whenever you're looking at a CPU, this is part of how we get such great performance. Whenever you're looking at CPU, its main memory access is much slower than a GPU's, right? It's like an order of magnitude slower. Actually, it might be 2 orders. But anyways, it's slow to get memory. So if you're going back and forth between your RAM on your computer, it takes a long time to actually execute the network. But what a CPU does have is L1, L2, and L3 caches, and those are orders of magnitude faster to access. So what we have is tensor columns, which are going to look at the hardware architecture of the CPU, figure out how much memory is available in each cache. Additionally, how fast the compute is, the CPU is actually processing at on the system. And what we're going to do is break each model down into tensor columns. So instead of executing layer by layer by layer, where we're likely going to blow out a cache and miss cache because the activations are so big, we're only going to take sections of each layer. And that way, we can actually stay in cache. So we can do multiple depth-wise sections. So looking across layers, get a really big benefit from sparsity because we're skipping a lot of those zeros for speed up. But additionally, get speed up because we're staying in cache. So you have memory speed up and you have compute speed up, and then you just tile that around the entire network. And then for the performance metrics, there's a question on if those are inference or training. Sorry, and yeah, just going back to those real fast, those are all inference results. So looking at this is all inference. So deep sparse, what we're focused on right now is inference performance and making that cheaper and faster to do. So we haven't focused yet on training, but this is all once you have a trained model and now you're ready to run it and you need to run it faster, or you just need to run it cheaper or more scalable, then you're going to plug this in and it's going to make it much cheaper, much more scalable to be able to run, and also enable you to be able to just run it on your laptop instead of having to keep it on an expensive GPU that you trained it on. Yeah, all great questions. Any other questions? Does it need retraining? So that is also a great question. Let me just go back to this slide. Sorry, Zoom's getting in the way. Got to find my slideshow. All right, there we go. Yeah, so great question. The post-training and one-shot does not require retraining. So this is all just going to be applied after training and trying conversion. That's where we're pushing a lot of research around right now. Training aware does require retraining. So what we're actually going to do is after you have a converged model, then we're going to train for probably a third of the time or half of the time that it originally took to train. We're going to train for that time to do the optimization. And then sparse transfer is retraining. It's just refine tuning. Yeah, great questions.
Just one more question, Mark. So the retraining question was associated with the performance benchmark for the inference metrics. So but those inference metrics that you show, like the performance boost part, are those like, are you just like sparsifying the retrained model? And is there any retraining after that, like after the sparsified model?
Gotcha.
Yeah, these ones.
Yeah. Let me get the cat out of the way. Yeah, no, that makes sense. So for the retraining, so after you sparsify it, you're done retraining. Technically, if you want to do the sparse transfer on it, then that would be considered another retraining. But if you're just looking at just optimizing for a single data set, then yeah, it's just take your converged dense model and then prune and quantize it with some extra retraining after that. And then you're good to go. In terms of the performance difference, so all of these performance metrics, these were applied with a training aware approach to be able to leverage that. Actually, I should say, image classification object detection aware, the NLP results, those were actually through sparse transfer to be able to do that. Our one-shot results that we have currently and that we haven't released yet if we're getting to 8x on ResNet 50, we can get to about 4x with one shot and maintaining the same accuracy. So it's on that level. So, a little bit slower, but in terms of the inference speed, but much faster to apply, and you don't need to retrain.
Okay, thanks, Mark. Great presentation.
Yeah, absolutely. All right. Well, thank you, everyone. And I'm going to sign off for the night. Have a good night.